So thanks very much for that introduction and for the opportunity to come and talk to you. I believe that one of the big issues in science today is to try to communicate these issues to the general public, hopefully in a way that is both rigorous and understandable. And so that's what I'm going to try and do. So what I want to do to begin with is to try to get you to appreciate the truly global nature and scale of this issue, to understand what is happening and why, to look at some of the scenarios for the future and how mitigation or addressing climate change will affect those scenarios, and very importantly, to get you to appreciate to some degree the uncertainties in those predictions and their significance, because the uncertainty is at least as important as what we think might happen. And then to consider it from a perspective, a risk perspective, because this is what it is. It's what we are trying to do is to mitigate future risk in an area of uncertain and incomplete knowledge. So just a few things. I put this slide up. It actually resonates with what we were talking about this morning about our common home. This blue blob in space, for which, as far as we know, there is not another one like it for several parsecs in any given direction, is where we live. The picture is from the moon. The average temperature on the moon is minus 14 degrees C. Sorry, minus 23 degrees C, whereas the average temperature of the Earth is plus 14. There is a reason for this difference in temperature, and the reason is the atmosphere as an insulating blanket. So when we are considering global warming, what we're talking about is the heat budget of the Earth. How much heat it receives, how much heat it retains, how much heat is lost to the surrounding space. The moon doesn't have an atmosphere. It's the same distance from the sun, and the difference is the insulating effect of the atmosphere. When we're considering climate change is different from global warming, because what climate change is the way our climate patterns change in response to the change in the heat budget. The weather is what we get. The climate is the range of weather that we can expect from year to year, season to season, from extreme to extreme. Sometimes we have a long run of frosts that we haven't encountered for many years, well, at least in Canberra. Other times we get some extreme heat, which we haven't seen for several years, but that is part of the normal climate. So when we talk about the climate of a region, it is the range of weather that we expect. The weather is what we get on any given day. And it's important to make these distinctions, because when you look at a picture of the Earth like this, you see pictures of swirling cloud, which indicates that in fact the atmosphere is turbulent. It is constantly churning. And the variability of the weather that we see, or the variability of the climate, is due to this turbulence. And in fact, this variability is affected by the fact the Earth, any part of the Earth, heats up and cools every time it rotates. It cools from season to season. Different parts of the Earth, because of the distance from the sun, receive different amounts of heat. And so that creates the turbulence in the atmosphere. A bit like when you're boiling a saucepan on a stove, when you see the turbulence in the water is a direct result of the input of the heat. And of course, when we're talking about climate change, we have to see through this variability and look at the underlying issues which are driving it. Now, there's another view from space. And this is the Earth at night. And what it shows is, over vast parts of the Earth, our technology has developed that we are permanently illuminating the Earth based on our fossil fuel. The density of the lights tells us three things: the density of the population, the sophistication of the technology, and the affluence of the people who live there who can afford this technology. And the point being is that all of these, and behind here, behind these lights, is industry, is transport, fossil fuel usage drives it all. Oil, gas, coal. Some places it's nuclear and other things. But the point being is that it is our industrial development since the industrial age that has led to the lifestyle that enables us to sit in comfort in this building at 22 degrees, where it's probably 29 degrees outside, and all of that is driven by fossil fuels. Here's another version of that slide. And this time the satellite imagery has been processed to reveal the fires that arise from land clearing. So in the previous slide, you will see Africa is blank. Northern Australia is blank. But what happens when you process there, those red areas are areas of slash and burn agriculture, of spontaneous natural fires. The green areas are areas where gas production, gas produced from oil fields is being flared and into the atmosphere. And some of the blue areas in the ocean are where there are fishing fleets, all with lights on, with burning diesel oil in engines and illuminating the fishing. The point is that there is hardly a part of the planet where mankind is not having an impact, whether it be through use of fossil fuels, or whether it be through slash and burn agriculture, or whether it is man-made or naturally occurred bushfires. The result of all of this activity has been the release of carbon dioxide emissions into the atmosphere. So this tracks the CO2 emissions in terms of gigatons, which is billions of tons of carbon dioxide per annum into the atmosphere since the Industrial Revolution. And the immediate thing that you see is it all took off after 1950. So that's within the lifetime of most of us in this room. And the point being is that at the bottom of the slide you will see that in 1950, at a population density of population of 2.5 billion, the energy demand per person was 10. I'm not going to go through all the units. In the population, in 2000, the population is 6 billion, and we have an energy demand per person of 20,000 kilowatt hours on average, which is a factor of 5. So energy demand has gone up by a factor of 5, which has resulted in CO2 emissions basically going up by a factor of 5 since the 1950s. And of course, a lot of this has been to do with the development of our modern technology in the Western world, and now increasingly technological developments in India and China. So the point that I want to make is, in addition to these, the others on this slide is things like cement manufacture. To make cement, you heat limestone. When you heat limestone, you release CO2. So all of our industrial process, the conversion of iron ore to iron and to steel, the conversion of bauxite to aluminium, all involves the release of CO2. That peak in the land clearing, which is at the bottom of the slide, land use change, was in 1998 when we first had the extensive land clearing in Indonesia, and you recall that the pit underlying the forests that were being cleared caught fire and resulted in tremendous pollution over Singapore and Malaysia. For those who've been following the news, we are into a second Super El Nino. The last one was 1998, and I don't know whether the severity of the current pollution going over Malaysia and Singapore is the same as 1998, but it could well be. So what happens to this carbon dioxide? Well, it becomes part of the natural carbon cycle. This is a very simplified version that shows the actual transfer of the billions of tons of CO2 between the different reservoirs of carbon on the planet. So in nature we have reservoirs of carbon in vegetation. In the ocean we have it in the form of dissolved carbon dioxide and algae and things that live in the ocean. In the geological area we have it as fossil fuels and as limestone and so forth. And in the atmosphere, of course, we have CO2. So what is happening is that we have been transferring from the geological reservoir of CO2, of carbon, to the atmosphere in a geological instant, a vast amount of carbon. So ever since the Industrial Revolution, and since we started exploiting fossil fuels, but particularly since 1950, we have actually transferred carbon from the geosphere, or from the rocks, into the atmosphere in a geological instance. About, unfortunately, I didn't realise that, but the arrow on the left has got chopped off. Excuse me for that. That number up there is 32, so there's 32 gigatons of carbon dioxide being emitted every year between 2004 and 2013 on average. About 10 of it goes straight back into the ocean. The land soaks up the vegetation, soaks up about 10. Land use change releases another 3, so land clearing releases 3. So the net result is that we're accumulating about 15 gigatons, 15 billion tons of carbon in the atmosphere every year. The result is the concentration over time of carbon dioxide in the atmosphere is going up. So these are the direct measurements that were initiated in the 1950s by a gentleman called Keeling. The observatory is on top of the extinct Kilauea volcano in Hawaii, and what you see is a progressive change in CO2 content. The annual wiggle is due to the seasonal difference between the uptake of CO2 by plants in the northern hemisphere, where all the land mass is, and the difference in the winter. Okay? So what happens is you get this annual wiggle. Measurements taken in the southern hemisphere lag behind this because most of the activity is in the northern hemisphere, and it takes a year or so for the atmosphere to totally mix. So when we tack this on to what we see in the bubbles and ice cores, where you see, so people have drilled in Antarctica and the Greenland ice cap, and in the layers of snow and ice there are bubbles that are trapped. So they measure the atmospheric composition trapped in those bubbles, and they measure the CO2 content. And what you see now is 600,000 years of Earth history where changes in CO2 content of the atmosphere. And the ups and downs coincide with the various ice ages. But as we come into the modern day, you can see that we are far, far above anything that has been happened in the last 600,000 years. So when I say we are transferring the CO2 from the geological world from the geosphere into the atmosphere in a geological instant, that vertical line is telling you what that geological instant is. It's unprecedented in Earth history for a long, long time. One of the first consequences of dissolving CO2 in the ocean is that the ocean is becoming progressively more acidic. So the pH of the ocean is changing from around 8.2 to 8.1. Now that may not sound much, but it's a logarithmic scale, and those of you who are gardeners will know the effect of pH on plants. And one of the consequences is that as CO2 dissolves in water, you produce carbonic acid, and making the water more acidic, and certain shell-forming animals are finding it more and more difficult to make their shells. And they tend to be small organisms and part of the marine food chain. So the marine food chain is potentially being disrupted. On a very practical level, on the west coast of the United States, oyster farmers are having to find that when they're spawning their oysters to create the spat, they are actually having to adjust the pH of the seawater in order for them not to die. And in fact, around the world now, we are beginning to see the effects, not so much in adult animals, but particularly in larvae and things, that in fact there are changes taking place that are due to this acidification. And this, of course, has got nothing to do with climate change per se. It's just merely a product of us putting more CO2 into the atmosphere and hence into the ocean. So what is this greenhouse effect that makes the Earth 14 degrees and the Moon minus 23? So when sunlight comes through the atmosphere is pretty transparent for sunlight purposes. And when the radiation hits a solid object or a dark object, of course, the wavelength shifts. You get some reflection straight out, but you get a conversion to a different wavelength. And we feel that if you stand in front of a brick wall on a sunny day, you can feel the heat coming off, which is the infrared radiation. When that happens, the infrared goes into the atmosphere. And virtually any atom, any molecule which has got 3 atoms or more absorbs the infrared radiation, and as a result it warms up and acts as insulation. So CO2 is one of the key gases that absorb it, but so is nitrous oxide, so is methane, and the CFCs, any larger molecule will do this. But importantly also water vapour. So but in fact, of course, water vapour, the humidity of the air increases as the temperature goes up. So the temperature goes up because of CO2, more water vapour gets included with the air and absorbs more of the radiation. So the water vapour in the air accentuates the greenhouse effect that is triggered by the CO2 and other molecules. So that is why the atmosphere is in fact an insulating blanket around the surface. And the basic physics was worked, the basic proposal for this was worked out in 1842. The actual physical measurements on the gases was done in 1872. And the first quantitative assessment of the greenhouse effect was done in 1898. So it's not new science, it's just that it hasn't been so important until recently. So what is the effect? For those of you who are not used to reading graphs, and I appreciate it, then I'm afraid I do have a few graphs and I will try to explain. So this is a record of the mean global surface temperature. So this is taking the Earth as a whole, averaging the temperature out over a whole year for all the different parts of it, and saying what is happening. And these are the raw measurements. These are the raw measurements. This is where we've taken 5 yearly averages, 60 months running mean 132, to take out some of the variation. And the variation is the natural variation in the climate that we were talking about. So, for those of you who are familiar, you know when you get an El Nino year, generally the world is hotter. When you get a La Nina year, the world is on average cooler. So that what happens is you're getting these changes in the circulation of the ocean, bringing cool water up, and that influences the climate for that year or for parts of the globe. And there are these what they call oscillations in the ocean currents that are taking place all over the world, and this is what affects this variability. Sometimes you get large overturns and there's a cooling effect, and this is why it's important to take very long-run averages. Short-term variations, which the deniers tend to use and say, oh look, it was hot there, it's gone cool, are irrelevant in this case, because we're talking about the long-run climate, not about the annual variations. The bottom figure is the Australian record, produced by the Bureau of Meteorology, with the same thing. The wiggles are the natural variation. Now in Australia, we have naturally a very variable climate, which I'm sure you all know. And we are particularly affected by La Nina and El Nino phenomenon. But when you take the running averages, we see in fact the Earth is warmed by about 0.8 degrees over pre-industrial times. Now there's a huge lag in the system. And one of the reasons is because it takes much longer to heat up water than it does air. I mean, you know that intuitively from our day-to-day experience. The amount of energy that it takes to heat a kettle of water compared with air is vast. In fact, the top 3 meters of the ocean has the same heat capacity as the whole of the atmosphere. But a lot of the heat is going into the ocean, as this curve shows. So, although we focus on the air temperature, the immediate effect is to heat up the ocean. And this is why it is such a long time lag in the process, because it takes time. So we're not in equilibrium with the CO2 in the atmosphere. Actually, we are still warming up given the CO2 levels that we have reached. But of course, the climate, the ocean, is actually fundamental to our climate. The ocean is what triggers a lot of our weather systems. So the fact that the ocean is warming up tells us that our weather systems are going to change. And we talk about the mean surface temperature of the Earth having gone up by 0.8 degrees. But in actual fact, when you deconstruct that, in fact, there are parts of the Earth where it's gone up a heck of a lot more. And this is a year's average temperature. So in the Arctic, for example, the temperature is 3 degrees already above the long-term average. You also see there a cool patch but in the North Atlantic between Ireland and Newfoundland, Canada. See that blue patch? I will come back to that in a moment, because that is a sign that something is happening that was the foundation of the movie The Day After Tomorrow. Okay? And so we'll come back to that. But the point being is that when the Earth warms up, and we talk about a 2 degree rise in temperature as being the maximum we'll add. What we're actually saying is that in parts of the world it will go up 8 or 10 degrees, not just 2 degrees. So, what is the consequence? Because the big impacts of global warming that we're seeing at the moment, they're in the Arctic. So the Arctic ice cap has diminished in size every year, basically, for the last 2 decades. This was predicted by the IPCC panel, but it's going much faster than anybody anticipated. So that it has declined in aerial extent by 30%. The Northwest Passage is now permanently open in summer. They're busy recalibrating how long the summer ice sheet will actually last. So it's not just aerial extent, it's also its thickness. And one of the consequences, if you do a Google search, for example, on walruses, you will find that in Alaska, there are huge aggregations of walruses forming on the seashore because they no longer have any ice to rest on in the summer. Polar bears, similarly, are suffering enormously because they're coming on land much earlier and staying much later than they would have traditionally done. And so on and so forth. So the ramifications of this are quite severe. When we look at the Greenland ice sheet, it has lost 3,000 billion tonnes of ice in just over the last decade. The Greenland ice sheet is now melting at a considerable rate. And that is the reason why you are getting that blue patch of cold water in the North Atlantic. Is the ice is coming off the Greenland ice sheet and cooling the ocean. Now, from those of you who have lived in Europe, you would know that the mild winters that the UK has, and also Norway, compared with its latitude, is due to a thing called the Gulf Stream. The Gulf Stream is a stream of hot, salty water that comes out of the Caribbean, moves diagonally across the North Atlantic, and moderates the weather in Western Europe. As the Gulf Stream moves north, this warm, salty water cools, and because of the slightly higher density, it begins to sink. It sinks and then forms part of the bottom water, which moves south through the Atlantic and all the way down into the Southern Hemisphere. The fresh, cold water coming off the Greenland ice sheet is diluting the salinity of the Gulf Stream so that this conveyor belt is slowing down. Now, in the day after tomorrow, they propose that it stopped completely and all the North American continent froze, and so did Europe. Now, we're not saying that that's going to happen, but the point being is that this could have a major effect on the climate of northwestern Europe. When, how much, it's still not clear. And this is one of these uncertainties. So as a result of both the heating of the ocean and the runoff of glacial ring, sea level is rising. So sea level rose at an average of just under 2 millimetres per year through the 20th century. So 10 years, 20 centimetres. But since about the mid-90s, it's been going up at 3.2 millimetres a year. Because initially it was just due to thermal expansion, and now as more ice is melting, you're progressively getting a faster and faster effect. So, what is the impact of warming on the climate in an area. So if you shift, if you imagine the climate as a distribution of weather that you can expect, and you shift the average temperature up, what that means is in the extremes, the frequency of the extremes get higher. And this is shown in this diagram. So as you shift the mean distribution, not very good with this one here, in that direction, what you see is you shift the extreme also, and you increase its frequency because more of the extreme is now into the bell-shaped curve. So this is why you get heat waves, more frequent heat waves. The mean distribution is shifting up, so your expectations of more extremes becomes high. The other thing that happens is because you're introducing more turbulence into the system, the actual distribution broadens out. So the variability increases at the same time as you shift it up. What that means is you can have an extreme heat event, but very occasionally you can still have an extreme cold event. Now, in North America over the last 2 years, you've heard of the polar vortex, where it's become extremely cold spells. Extremely cold, I think it's static electricity. Extremely cold spells because the polar vortex, which is the jet stream that circulates the Arctic in the winter and keeps the very hot, cold air trapped, has extended further south. But what keeps the cold air trapped in the north is the gradient, the heat gradient between the mid-latitudes and the poles. Because the polar areas have been warming up, the heat gradient has flattened, and so the jet stream starts meandering. And so the jet stream meanders further south and drags the cold air with it, which is one of the explanations as to why they've had these extremely cold spells in North America over the last couple of years. Now, it's still a subject of research, but that's one of the current thinking. So when we talk about global warming, that's one part of the story, that's the change in the heat balance. But what climate change is really talking about is the redistribution of the heat around the Earth as the boundaries between the existing systems change. So, the shift in the average number of day, warmest 1% of records in Australia, Bureau of Meteorology. So it's happening here as well. So we can expect longer, hotter periods when they do occur, and we can expect the temperatures to reach extreme values. One of the consequences for Australia is that the forest fire danger index goes up. So this is a change in the forest fire danger index in Australia as a result of global warming. Now in Canberra in 2003 we had those horrendous bushfires, and also of course on Black Saturday in Victoria a few years ago. The fire behaviour that was experienced at that time was unprecedented in both locations, and is to do with both the extreme temperatures and the extent of drying out. So when we're talking about drying out, it also refers to agriculture. So our farming is going to become more uncertain as the average temperature goes up. Because for those of you agriculturists know, there's a thing called the pan evaporation indicator, which is the rate at which moisture is evaporated. So we are going, the variability is increasing, so hotter is becoming hotter and drier, but because warmer air holds more moisture, when you get a low system, it holds more moisture, and we're getting more rain in areas where it rains. So, for example, this is the worldwide precipitation average, right, from 1900 to 2020, and this is put out by the World Meteorological Organization. And you can see that, post-1950, there are many years where, on average around the world, we're getting 2 inches more of rain. That's a lot of rain. That's a lot of rain. In Australia, what is happening is the southern part of the continent is drying out. So if you know anybody in Perth, you would know that they've changed what is an average rainfall in Perth because it is dried out to such an extent, and the runoff to the downs is such now that their desalination plant is in operation. I think 40% of the water in Perth is now being generated by their desalination plant. 30 or 40 years ago, that was not the case. Now, the population's increased, it's true. But the drying out of the southwest is extensive. It's also drying out in the southeast, progressively. And in northern Australia, it's getting wetter. So this is what we would call the southern wet season, which would be April to November. And in the northern wet season, which is October to April, which is the monsoon season, again, northern Australia is getting wetter, but we still see the drying out, the continuation of the drying trends in the southeast and the southwest. Climate change is not confined to poor countries. It's here, in Australia, and it's getting very significant. Loss events. So this is from Munich Reinsurance, the big reinsurers in Germany, who are the secondary insurers. So they're very interested in global trends of worldwide catastrophic events. And what you see here is a summary of the events from 1980 to 2014. But along the bottom is geophysical, that's earthquakes. So the earthquakes have stayed constant, which is not surprising. It's got nothing to do with climate change. The meteorological events, the hydrological events, and the climatological events, being heat waves, hydrological events being flood and mass movement, and meteorological events being tropical storms and convective storms, are all increasing around the world. So this is the increase in the variability. When it rains, it really rains, and when it's dry, it's really dry. But there's no guarantee that the boundaries of where it happened will stay the same from what it used to be. It's going to change. So, at the Copenhagen conference, they said, well, we must stop the world going into what they call dangerous climate change. And dangerous climate change was something that threatens food production and economic development. At the subsequent conference at Cancun, the most vulnerable countries said, no, it's got to be 1.5 degrees, we're already being affected. I must get it on. But so the tipping points for dangerous climate change are illustrated here. So I talked about the Atlantic thermal airline system. There's concerns that the Indian monsoon is deteriorating. The Himalayan glaciers, which actually supply the water through the summer months to 750 million people in Asia, are melting and retreating. The boreal forest, which is that vast taiga that extends across Russia and Canada, just below the Arctic Circle, is breaking up. Parts of it are dying. The population of moose in Minnesota used to be 9,000. It is now back to about 100. Because their environment is deteriorating. Tropical coral reefs will probably disappear, including our own Great Barrier Reef, because of the effect of coral bleaching and the effect of the acidifying ocean makes them more susceptible. So these are what you might call the physical tipping points that they're trying to avoid. But already the Greenland ice sheet is beginning to go, so some of this uncertainty is there. So social vulnerability, these are some examples, they're not by meaning the total, but say irrigation demand exceeding 50% of the seasonal water for use for agriculture in Victoria. I've told you that it's trying out. So on our doorstep, we are faced with this problem. We've heard about the depopulation of the Pacific Islands. Water shortages, malaria, because of this, as the temperature warms up, the malaria, the mosquito vector goes further and further. A destabilisation of the international order and world impacts on GDP. Now, the big problem is that we don't know exactly the timing of these events, and part of it is because of the uncertainty associated with some of these changes. So how you translate an emission scenario into a carbon cycle response and the climate sensitivity, the error bar on your projections gets larger and larger, and this is why the projections become riskier. But what we do know is that the warming is linearly related to the volume of CO2 that we emit. So this enables us to put a carbon budget. If we want to stay within 2 degrees, we can only emit, since 1870, 3,200 gigatons of carbon. We have already emitted 2,000. If we continue at that same rate, we will have used up the budget in 30 years. So this is why it's becoming a very urgent problem. So the IPCC runs scenarios, and they say, well, what would the carbon profile look like if you want to stay within 2 degrees? And the blue line at the bottom is what it's got to look like. That requires anything else, and the temperature goes above 2 degrees. And it's important to realise that when you say 2 degrees, what the IPCC say is there is a 66% chance that the temperature will be somewhere between 0.9 and 2.3 degrees. What that says, there's a 34% chance it will be outside that. And since we're already at 0.8 degrees, the chances are it'll be at the high end. So what does it mean on average? It means that by 2050, our annual global budget emissions must be no more than 9 gigatons, assuming a smooth thing, which is 1 gigaton per person, 1 ton per annum per person for the 9 billion people who are expected to be in the world in 2050. That requires the haves to have countries to reduce their carbon emissions between 25 and 40% by 2020 and 95% by 2050. The developing countries whose carbon emissions are less, 15 to 30%. Australia has the highest per capita emissions per person in the OECD. That leads you to because 1 tonne of carbon, according to a study from economists in the US, generates $58 worth of environmental damage. That actually means that Australians, indirectly, through their economy, are more responsible for environmental damage than any single member of an OECD country in the world. That is a very sobering statement. So, uncertainty as to the precise outcomes is all the more reason to act. We're presently on a trajectory to 700 parts per million in the atmosphere, which says there's a 66% chance that we've been 1.7 or 3.2. But there's also a 34% chance it will be outside of this range biased to higher values. At 700 parts per million, there's an 11% chance of a 6-degree outcome. When you do the probabilities. And we routinely insure against those level of risks in our daily lives. We take house insurance out. You might take life insurance out. Or anything. So the cost of climate change impacts is already $58 per tonne of carbon dioxide released in 2015. So therefore, Australia's annual emissions is therefore causing $3.2 billion worth of damage environmentally in this year. So what do the economists say? In the end, it's risk management, existential risk management, and it comes with an ethical component. Precaution is a prudent stance when uncertainties about catastrophic risks are dominant, as they are here. Benefit-cost analysis is important, but alone it may be inadequate simply because of the fuzziness we are dealing with analysing high temperature impacts. The appropriate price on carbon is one that will make us comfortable enough to know that we'll never get anywhere near 6 degrees, because that is certain catastrophe. And on a personal note, one of the reasons why I get very concerned about it is because I have 6 grandchildren. All of them will live towards the end of this century, and your children and grandchildren will too, and they will be bearing the brunt of it. So quite apart from the ethical issues concerning Pacific Islands and third world countries, we also have an obligation to our grandchildren. Thanks.